Okay, there are a lot of scenarios in science and in medicine which we are dealing with charged particles, and we can, apply forces on them. F equals QV cross B. Okay, so we can apply forces to them. We can control magnetic fields with a solenoid, for example, or straight lines or loops, and we can cause these charged particles to move based on this equation. Well, what happens if we are applying a magnetic field from something to a current? Okay, so that's this scenario. We've got a wire and current's flowing in it right now. There's a current flowing in this wire. Well, if you look at that wire and break a section into it, there's an amount dq right there. Now this wire is full of charge, but I'm going to just focus on that one. Now let's just suppose that I place this wire in a region of space where the magnetic field is everywhere going into the page. Okay, so everywhere the field is pointing into the page. This would be into the page. All right. And so if that's the case, and that's everywhere, not just at that point, but I'm just going to say it's in this region of space here, the B field is everywhere into the page. So that means that charge is moving with a velocity v right there, and the B field everywhere, so the B field even at that point right there, is into the page. So if I do my right-hand rule, I get V cross B, B is down, makes my thumb point up the page. Okay, so there's a force acting on it. Now I need to be careful because that's the force acting on just that bit of charge, and that bit of charge is stuck inside the wire, which means if that bit of charge gets pulled up, the wire is going to get pulled up. So I'm going to call that a DF because there's another piece of charge right here that's having the same force, and another one over here, and another one over, everywhere I break this entire up is full of DQs. And so to find the total force on this wire, I would have to integrate it. Whatever I got for DF, I need to integrate it over the whole wire. Okay? Now, generally, we've done a lot of integration problems, and we follow the same process, but we can come up with some pretty quick results when things are constant. And we're going to focus on those cases. So we're going to focus on the force on a long straight wire, or a straight segment of a wire. We assume the B field is constant and perpendicular to that wire, and then we'll find the total force. So if that's a DF, what I want to do is say DF is equal to DQ V cross B. Remember again that B is some applied V from sources other than these charges here, something else. Okay? Well, what is V? That's just dl over dt. If I say that this little piece of charge has a length dl, okay, I'm going to put a vector over it indicating that it's got a direction. dl is pointed that way. Okay, cross B. Well, I can just move this dt over, and I can say that's dq dt dl cross B. But what is dq dt? That is our current. That's the definition of current. So this equals I dl cross B, which is awesome because I can calculate current from using Ohm's law or something like that. I can control that really easily. In general, I can control this from a solenoid. I've got the equation to create a B field from a solenoid. And so I can now find the force acting on a piece of a wire from this simple equation, just knowing the current flowing through the wire and the B field from something else acting on that wire. Okay? Now note, that's still DF. And so if I was going to find the force along this whole thing, if I assume B is constant everywhere and constantly perpendicular everywhere, well, I is always constant in a wire. So then I can say F is equal to I, and then integrate DL cross B, which if that's constant, then this just becomes ILB, okay, where L would be the full length of the wire. So that is the force on a current carrying wire of length L from B being some sources somewhere else. Now the text does a nice derivation to show, well, what if this B field is from another wire, which we know the B field from a wire. So what if we have these two wires sitting here, and we want to say, what's the force between them? Well, it's going to be the B field from this wire here, which we can calculate. There would be a B field at this location due to this wire, and then multiply that through this equation by the current flowing through this one and its length. We could reverse that and we'd find that that obeys Newton's third law as it ought to. The currents are going to be, they could switch places. I1 and I2 will be a product. So this is a really cool example, but I'll leave that derivation for the text. But the point is we're just looking at moving charges, and the B field's from something else acting on it, but when it's in a wire, we can just now focus on the current through the wire.